Hey guys, welcome to section 4 of my course on quantum mechanics. And in this section we are going to be dealing mostly with the Schrodinger equation, some techniques to solving it, solutions for it in particular situations. Now the first thing I'll say is before you watch this video, other than knowing what we did in sections 2 and 3 and 1 of course, but the important thing also is for you to review the video if you're not super comfortable with them. Review my video on derivatives, which will cover partial derivatives, and also review my video on differential equations, because those will be the things from those videos will be used in this video. And I'll have those linked in the description here. Okay, so the other thing is a quick notation note that I have written here this capital psi, the capital Greek letter psi, and the difference between writing the lowercase psi and the capital psi is, and I show it here, what the argument of the function is, right, and the argument, what the input is. For capital psi is going to be a function of both position and time. Lowercase psi, how we've had it before, this wave function is just a function of position, right? And so that's how I will draw the distinction between whether something's a function, or the wave functions of both position and time, or just a wave function of position. Lowercase psi will be of just x, capital psi will be of x and t. Okay. And now I also have written the Schrodinger equation twice. One is sort of this blue one over here. I just want you to see it, because that's a lot of the times people write this equation. Sometimes they'll write it with just a lowercase psi, but I want to make sure I'm being very consistent with the notation, that this capital psi is a function of x and t, right? Some people will use psi for just a lowercase psi for both a function of x and t and a function of just x, but you will hopefully see in the next few videos why I like to draw the distinction, because we will be dealing with both separately. But so this is how I like to write the Schrodinger equation in general. It makes it look a lot nicer without all of the, of x and the of x and t. So I just want to show this so you can kind of see it in its more compact form. But now I'm going to get rid of that. So we can start working on this the Schrodinger equation. Now remember, we cannot just solve the Schrodinger equation once and be done with it. And that is because it has this term right here, this v of x term, which is the potential energy function. And that is going to differ depending on what forces we have acting on the particle, right? So we can't just solve this equation without knowing what the potential energy function is, which would make sense. We can't just know the wave function without knowing what forces act on the particle, right? That would be like saying that the forces on the particle don't matter, and they of course do, right? So that's how we incorporate the forces in this Schrodinger equation. However, there are some steps we can take in order to make this equation easier to solve and even start getting towards solving it. So that's what we're going to be doing in this video. Now, some of these steps are a little bit tricky, so if you don't quite understand them, either watch the video again or take my word on it. Of course, I'd love if you could understand all the steps, but depending on how great you are with the math, it may or may not be possible to get every single step in this process. Okay, so the first thing we're going to do, and it may not make a lot of sense right now why we would be doing this, but I'd like you to just trust me on this, that this is a good first step to take, and then we'll see where it takes us. Okay, so also if you have taken any kind of course of partial differential equations, this technique will be very familiar to you. But if not, which I'm guessing a lot of the people watching this video will not have had a formal knowledge of partial differential equations, so this may not seem as intuitive to you. Okay, so the first step is I'm going to say let capital psi of x and t let's just say, right, and this is not necessarily true for every function of x and t, but what if? This is sort of like a what if. What if this function could be broken up into two parts? It could be a function of x times a function f of t, right? This now I just want to look at what would happen. What would happen if this equation could be written like this, right? Well, now let's plug this back into our original Schrodinger equation. We have negative h bar squared over 2m d squared by dx squared. I'm going to, for right now, just because it's going to get very, very difficult to write all of the of x's of t's, I'm going to leave them off for right now. I'll put them back in a little bit later. Okay, so this is psi times f plus v psi f equals I h bar d by dt psi times f. Right? Well, now we know how partial derivatives work, right? And if I have a function of x times a function of time, right? Time is considered just as a constant, right? When we're taking a partial derivative with respect to x, time is treated like a constant, right? And we can take constants out of the derivative. Same thing when we're taking a partial derivative with respect to time, right? X is treated as a constant, so we can take that constant out. So what I'm saying here is, right, this is a constant with respect to x, and this psi is a constant with respect to t, so we can take them outside of the derivative. So let's now rewrite our equation, negative h bar squared over 2m. Now I'll write our f times d squared by dx squared psi plus v psi f equals I h bar psi d by dt of f. Right? Okay. So now our next step is going to be dividing this whole equation, dividing every term. Remember, we have to divide this term and this term and this term, all by psi times f. Right? And notice what this will do. Right? When we divide, we have to divide every term out. Now, when we take this first term, and I'll expand this term by term, going to get negative h bar squared over 2m. Now, this f is going to be divided out, right? But the size will not be divided out, right? Because one is inside the derivative, one is outside of the derivative. We can't just, divide. We can't just take like, the derivative of some function and then divide it by that function. It won't cancel out. That's just not how derivatives work, right? Because this is operating on this. Hopefully that makes sense. If you're familiar with derivatives, and maybe try an example, try like taking the derivative of x squared and then dividing it by x, and then dividing the whole thing by x squared, you'll find out that it is not just the derivative. It's not, they don't cancel. You don't just get the derivative of 1, right? Hopefully that makes sense. Just if, that's how derivatives work. Okay, so the f's will cancel out, but we'll be left with a 1 over psi here. And actually here I'm going to write 1 over psi of x, right, times d by dx of psi of, d squared by dx squared of psi of x. Right, this next term, both psi and f get can be canceled out. So this is plus v of x equals. So now this term, the size will cancel, the f's will not. So I h bar over f of t d by dt f of t. Okay, so now we have written the Schrodinger equation in this form if the solution, it's called a separable solution, where we can separate the psi of x and the f of t. Now here is the difficult step sometimes to grasp of this. Here I have a function of just x, right? This side of the equation, the left side of the equation, it only depends on x. The right side of the equation only depends on time, right? Which, now, if we think about what this implies, these have to be equal for any x and any t, right? But what happens if I just change x a little bit? Well, if I just change x, but I don't change t, if I don't change t, the right side will not change. But if I change x, this left side could change, right? Same thing if I just change t and I don't change x. This right side would change and the left side wouldn't change, right? The only way for this to work is if both sides are equal to a constant, right? If we have both sides here, write this in green, both sides have to be equal to a constant, right? Because otherwise, if they weren't equal, if say this right side was not equal to a constant, and we changed t and we didn't change x, the equation wouldn't hold anymore. Same thing for changing x and not t if it was not equal to a constant. So the only way this equation can work is if both sides are equal to a constant. And let's just say we can call this constant whatever we want to call it, right? Oftentimes people will use c for a constant, but just because I know where we're heading with this, I'm going to call this constant e. Now this constant doesn't mean anything right now. All we know is it is some constant, but it turns out it will have some physical meaning, and that physical meaning will have something to do with energy, right? Hopefully we can kind of see where this is going. But so yeah. Okay, next, I'm going to erase this stuff up here to make sure you have everything down. And I'll bring this back up here. So remember, and I'm going to put this up here again, this is the case if. This is all if capital psi of x and t could be separated out into psi of x times f of t, right? This is just maybe I call it a what if situation, you know? But it turns out this situation will actually have some significant consequences. Okay, so now, because both of these sides are equal to this constant e, we actually have two equations here. We have, and I'll write one of them in blue. Right, we've got negative h bar squared over 2m times 1 over psi. I'll get rid of the of x. Although, here's one important thing that we can do now. We've been dealing with partial derivatives, right? But that's only because we've had both a function of x and a function of time, right? Now that, right, the equation that I'm writing in blue will only have x in it, we don't need partial derivatives anymore. We can just work with an ordinary derivative, ordinary second derivative. So I'll write d squared by dx squared psi plus v equals e. Right? This is our x version of the equation. Remember, we can just use ordinary derivatives because we don't have any time to deal with. Now, let's write in this pink, let's write the time part of the equation. And again, we'll be able to h bar over f, get rid of the partial derivatives because we're only dealing with time. D by dt of f equals e. Okay, so I'm going to start with this blue equation because there's less we can do with it. First thing I'm going to do, and actually last thing I'm going to do, is multiply everything by psi, right? Negative h bar squared over 2m d squared by dx squared psi plus v psi equals e psi, right? And this is going to be called the time-independent Schrodinger equation, right? And the other Schrodinger equation we had before, in the more general Schrodinger equation, is called the time-dependent Schrodinger equation. Hopefully you remember what that is. I know I erased it, but hopefully you have it written down, right? And this is the time-independent Schrodinger equation. We cannot go any farther with solving this equation without knowing what the potential energy function is. However, notice, in this case, right, this is the energy eigenvalue equation, right, that I have down here. Even though it doesn't have the partial derivatives, we don't need the partials because it's only a function of x, right? And so this, really what I'll call it is, I'll call this is psi e, which is the wave function of x with a definite energy, right? And so that is, in fact, our energy eigenfunction in x, right? And it actually looks like this equation will be our energy eigenvalue equation in just time, right? If you look at this one. And, in fact, we can solve this differential equation, right? If I rewrite it like this, I h bar d by dt f equals ef, right? Or, and then I write d by dt f equals, and now when I divide by IH bar, this is E over IH bar, although, if you remember, dividing by I is the same as multiplying by negative I. I believe I mentioned that in the video on complex numbers, but if you just need a quick proof of that, right, if this is more of just a verification, but if we write that 1 over I is equal to negative I, right? Well, what happens if we multiply both sides of this equation by I? 1 over I times I is 1, and negative I times I is 1, right? And so this would show. Also, if you think about the cycle, right, of the powers of I to the 0 is 1. I to the negative 1, if you just work that cycle backwards, would be a negative I, and I to the negative 1 is, of course, 1 over I. Right? So this is E over IH bar times F. I want to write that in the pink color. Times F, right? Which is negative I E over H bar F. Right? Which is, of course, E over H bar, we know, is omega, right? Because of the de Broglie relation. So this is minus I omega F. And this equation can be solved. F equals some constant times e to the minus I omega t. And actually, sometimes people will write this as c e to the minus I e t over h bar. But I personally prefer to write it with minus I omega t. Right? And now the last thing we can do here, well, actually yeah, so the last thing we can do here is notice that we have a constant out in front of this. And it turns out because this is a linear differential equation, and you can show this on your own just by, if I have psi times e being a solution to this equation, 2 times psi, it's not psi times e, psi e being a solution of this equation, 2 times psi e would also be a solution to this equation. In fact, any constant multiple of psi e would be a solution, and any constant multiple of any solution to this equation will also be a solution. Right? So when we solve this, we'll get some constant out in front, and we have a constant from here, right? And we're just multiplying them together, so we can just combine the constants, because we'll have a constant from this equation, and then this constant multiplied together. So it turns out what we like to do is basically get rid of this constant over here. We basically say we absorb that constant into this equation, right? Because we don't need the constant in two different places. We can just have the constant as what we get when we solve this equation, when we solve the time-independent Schrodinger equation, right? Hopefully that makes sense, that we don't need both constants, so we just pick one of them to use, and the other one we write without it. Right, so the general form of this separable solution, which I will call psi, or capital Psi e of x and t, right? This is a solution to the time-dependent Schrodinger equation, the full Schrodinger equation. This is going to be psi e, little psi e of x, right, which we get from this time-independent Schrodinger equation, times f of t, which is e to the minus I omega t. Right? So this is a solution to the time-dependent Schrodinger equation. It is not all of the solutions, but I will show you, in fact, how we can get from this solution to all of them. Now, I've kind of implied it with writing out it like this, but this capital Psi e is actually the general energy eigenfunction for right, and I show that in our next thing, right? So I wrote that we have this energy eigenfunction phi sub e is really just our capital Psi e, right, which is lowercase psi e times f, right? And I show that, I just show that it works for these two energy eigenstates, because remember, these are the criteria, these two equations, one in green, one in orange, are the criteria for being an energy eigenfunction. We showed that back in section 3. These are the two criteria you have to have, and because of how partial derivatives work, and we can take things out of the partial derivatives, we can show that in fact, right, and we get back to the equations that we had that defined this psi e and this f, right? So this work, hopefully you can see that it shows that this capital Psi e are the energy eigenfunctions. So the energy eigenfunctions solve the Schrodinger equation. Now, we can use one other thing that we know about, because remember, these are Hermitian operators. Also note, we do have to have the partial derivatives here because they are acting on they're acting on functions of x and t, right? So now we know that because energy operators are Hermitian, right, we know that the eigenfunctions have to form a complete basis, that any wave function can be expressed as a superposition of energy eigenfunctions. And given that, we also know, right, that the Schrodinger equation is what is called a linear equation. So I'm going to write this down here, where I have written, well, I'll write down the Schrodinger equation. Negative h bar squared over 2m d squared by dx squared psi of x and t. Actually, I won't write the x and t. Plus v psi equals I h bar d by dt capital psi. Right? And now we can show, because derivative operators, because of how they work, right? We can show, in fact, that if I have two solutions of this equation, psi 1, psi 2, right? If both of these solve, or I'll write up here actually. If psi 1 and psi 2, that's not looking great. Sorry about that. Okay, if psi 1 and psi 2 both solve the time-dependent Schrodinger equation, then psi 1 plus psi 2, or really, right, plus psi 3, and there can be constants here, so C1, C2, C3, right, plus dot dot dot, also solves time-dependent Schrodinger equation, right? And we can show that, you can show it with just two. That if you have that, because the derivative is a linear operator, constants can be pulled out of it, and also the sum, the derivative of a sum is the sum of the derivatives. It's pretty easy to show that this statement is true. And so I'll leave that up to you guys, or you can just take my word on it, that a sum of solutions to the time-dependent Schrodinger equation, they don't even have to have the same energy, right? Nowhere in this proof would we use the fact that they have the same energy, so they don't have to. Any sum, or a linear combination of time-dependent Schrodinger equation solutions is another time-dependent Schrodinger equation solution. And we know that since any wave function, right, that can exist, right, that any wave function that it can physically exist, can be a sum of energy eigenstates, right? That is the completeness of the energy eigenfunction basis, right, because they're linear operators. And therefore, the general solution to the time-dependent Schrodinger equation, the general solution of the energy eigenvalue, or of the time-dependent Schrodinger equation, will be a sum of the separable solutions. Right, so this is a sum over all possible energies, right? You could do sort of a sum integral here, right, of the functions with a definite energy, right? And then there's a constant out front. So a linear combination, some kind of superposition of the functions with a definite energy, those solutions form the general solutions to the time-dependent Schrodinger equation, right? And that's because the equation's linear, and either way that any wave function can be written as a superposition of energy eigenstates, right? And so now we have found the general solution, and I'll write this in a slightly more suggestive form, right? Where say we have, and this will be a lot of the times the case, where we have discrete energy levels, right? So we know that capital psi sub n is equal to little psi n of x times e to the minus I omega n t, with energy En equals h bar omega n, right? This should hopefully make sense. This will just be the nth energy solution to the time dependent Schrodinger equation. It's a separable solution. Well, we know that the general psi x and t, the general solution to the Schrodinger equation will be a sum of these solutions. So a sum over all the possible values of n, psi nx, we'll have a cn out front, psi nx e to the minus I omega n t. Just summing over all possible energies, and then we have a function of both position and time. And of course, we have to have the condition, the sum over all values of n, cn norm squared equals 1. That's our normalization condition, as well as knowing that these psi of x's have to be normalized. Right? And so the last thing I would like to show you is the fact when we're normalizing solutions to the time-dependent Schrodinger equation, right? When we're normalizing these separable solutions, all we actually have to do is normalize the psi of x, right? Because if we think about capital psi norm squared, this is psi n norm squared e to the minus I omega n t norm squared, right? Or actually, I'll just write, instead of all the n's, I'll just write e. I think that makes it more general. Psi e, and then, right? But e to the minus I omega t, the norm squared of that, right, is 1, right? We know that from our video on complex exponentials, that the norm squared and the magnitude of a complex exponential is just 1, right? And so the norm squared of capital psi e is the norm squared of lowercase psi e, right? So the condition, the integral from negative infinity to infinity of capital psi e norm squared dx equals 1, right, is the same condition as the integral from negative infinity to infinity that lowercase psi, right? We don't need the f of t part because when we take the norm squared, it just becomes 1. Right? So when we're normalizing these solutions, we only need to normalize the part, the x part, the solution of the time-independent Schrodinger equation. So I will leave you with this. Our process now. We actually found a process. You may not have realized it, but we found a process for solving the time-dependent Schrodinger equation. Well, what we have to do is we have to find all the solutions of the time-independent Schrodinger equation, which will give us these psi n's, right? We find the lowercase psi solutions to the time-independent Schrodinger equation. We find the energy, which will give us this e to the minus I omega t, right? Because omega is e over h bar, right? And then we just take a superposition, and we have found the general solution to the time-dependent Schrodinger equation. So that should be impressive. To find the general solution to the time-dependent Schrodinger equation, we just have to find all the energies of the time-independent Schrodinger, all the solutions to the time-independent Schrodinger equation, and the energies corresponding to those solutions. And then all we have to do is take that superposition. And you may notice that I haven't talked about continuous superpositions, and we will actually get to that in a few videos. So if you're thinking about that, just wait for a few videos and we will get to doing that, but I didn't want to put all of that all in one video.